The next part of section 6.3 is volume by disk. And I think volume by disk is much easier than 6.3a. And the section 6.3c, which will be volumes by washers, is just a little bit more difficult than this one. But again, it's a little bit easier than 6.3a because it's easier to visualize these than it is to visualize the 6.3a problem. So volume by disks. The way we get a volume by a disk, or in the next section also a volume by a washer, is these are solids of revolution. No longer am I going to take something that's going to have like squares or isosceles right triangles or equilateral triangles as their cross sections. In this one, what I'm going to do is I'm going to take a single function, any single function, f of x, and I am going to take that function and either revolve it around a horizontal line or revolve it around a vertical line. And so in the first case, I'm going to revolve it around the horizontal line. And if I revolve it around the horizontal line all the way around, what I end up with is a whole bunch of circles. Okay? And those circles, because they are solid, we call those disks. Okay? A circle is just all the points on the outer edge. A disk is all the points plus all the points on the inside. So what I want to do is I want to find the volume of this. Well, hey, look, I've got the same circular cross-section. And if I slice this perpendicular to the axis of revolution, so if I slice this up into a whole bunch of little tiny pieces, each one of these is going to approximate a cylinder. Okay, and we know what the formula for the volume of a cylinder is. Hey, it's its base area times its height. Well, the base area here is a circle. So it's the formula of the base area times the height. Well, a circle's base area is pi r squared. And in this case, my height is going to be going from here to here, the thickness of that region, which would be dx. Okay, and again, we can go from A to B. We don't have to take the whole curve. We can just take part of the curve. Well, let's look at what r is. Well, r is the distance from the center of rotation to the top of the curve. So r is equal to the absolute value of the center. We'll put the top minus the center. Well, the top in our case right here is f of x. Our center is 0, so my r is f of x. So the formula I'm going to use here is pi f of x squared dx. And that will give me the volume of that solid of revolution. Okay? I also said that I can rotate that solid around the y-axis. So I'm going to, again, just draw an arbitrary function. Let's just do something that looks almost like the square root function. I'm going to rotate this around the y-axis. It's going to give me that part. And I end up with a whole bunch of circles. Okay? And again, this one, my radius is the distance between the center of rotation and that curve. Okay? Because I'm rotating it along the y-axis, the formula that I would get for this one, I'm going to call my lower limit, my starting point here for y, I'll call that C and D. Where let's say here, I'm going to call this A and B, like I did here. So C and D of pi r squared is going to be an f of y. Function in terms of y, dy. Okay? Those are the two formulas that we're going to use. Okay? This f of y squared and the f of x squared may change if my center of revolution is not the x-axis or the y-axis. You just need to remember that the radius is the distance from the center up to the top of the curve, or the distance from the center to the original function on the right-hand side. So these two formulas, or actually I only memorize this one, because these two I can come up with from this one, noting that r is equal to the top minus the center. That formula is the one that you need to memorize to do solids by disks. So the next thing I'm going to do is I'm going to do several examples of finding volumes of disks, solids of revolution using the disk method.